Okay, let's take a look at torque. Torque builds really nicely on force analysis, and I always like to remind students that torques are caused by forces. Sometimes folks think that torques are like a different kind of force or something, but the idea of torque, which is where we start paying attention to where forces are applied, torques are still completely force dependent, right? So let's just take a moment here and remind ourselves that in order to calculate torque, which is vector, we take the vector product of r, which is a vector going from the axis of rotation to the point of force application, and cross that in with the force that's being applied. So you can see that torque is really torques happen because forces are present. Forces are what make everything happen, right? All change happens because of forces. And then we have what's really useful is, of course, second law, Newton's second law. Oops. For translation. And then we have, of course, Newton's second law for rotation. Okay. And all of this is applied in much the same way we've been doing for most of this class now, as you've, a lot of our focus is on Newtonian analysis. So this will be the same. All right, so let's look at the situation here. We start with something really simple. We have just a cord that's attached to the pulley, and then there's an applied force on this block M here. The applied force is pulling everything to the right. This is frictionless. I'm starting off really simple. And all we're asked to determine here is the angular acceleration of the pulley. So take a look at what we're given. We're given the radius and moment of inertia of the pulley, the mass of the block, and the applied force on the block. And again, there's no friction at the interface. So as always, we start with our free body diagrams here. So what we will need is a couple things: free body diagram for the block, and then we are going to have a torque, what I call a torque diagram for the pulley. So we'll talk about that in just a sec, but let's just stay with what we know. We should be pretty good now at these free body diagrams. So if I look at my block here, identifying forces, what are the forces on my block? I have the applied force that's given, being called P. Normal force, the surface underneath the block, there's no friction. That surface is not exerting any friction. So that's it for the surface touching it. The only other thing in contact is this cord going to the left. I'll call that tension T. And then, of course, the weight of the block downward. All right. And then I'm going to go ahead and put a coordinate system on here, rightward and upward positive, again, attempting to align my positive with the direction of acceleration. So that's it for the block. Now let me look at the pulley. So a torque diagram, what that's about really is now you draw the shape of the thing that you're analyzing, because, and you might be like, why do we draw the shape? We draw the shape because now we're very interested in where the force is applied. Remember that when you look at the equation for torque, the r is all about where that force is applied. So the r is the vector that goes from the axis of rotation to the point of force application. So first, let's look at force application on the pulley. So just have a look at the pulley for a moment, and we're looking at what's touching the pulley. Well, a couple things are, again, in contact with the pulley. One is this brace here that's in contact with the axle, right? So you could say, well, the axle is supporting the pulley. The axle, though, is true. That is happening on the pulley. So there is, like, you could consider a normal force on the pulley, right? So there is that normal force. The normal force, where is it acting, though? It's acting at the axis of rotation. So since it's acting at the axis of rotation, the R value for that normal force is going to be 0. Remember, R is a vector that goes from the axis of rotation to the point of force application. So if the force is applied at the axis of rotation, you don't have any torque. That's like you trying to open the door by pushing on the hinge side. right? If you push right on those hinges, I mean, you could do that all day. That door's not going to open. So the only way that you have a non-zero torque is if that force is applied off axis or some non-zero distance from the axis of rotation. If you look at the pulley, we see that there's a normal force and then obviously the weight of the pulley, if you were to draw a free body diagram of that pulley, right? The pulley has weight. We know that. It has a moment of inertia, I, so we're not talking about a massless pulley anymore here. We're talking about a pulley that has mass. So the gravitational force on the pulley, its weight will be directed straight down. And so the pulley is, we can assume that it's some uniform kind of pulley, right? That the mass is uniformly distributed. So the weight of the pulley is acting on the center of mass of the pulley, which is the same as the geometric center, which is where the axle is. Okay, so what all that means is that neither the weight of the pulley nor the normal force holding up the pulley cause the pulley to accelerate. And if you think about it conceptually, that makes sense, right? Like just because you have a pulley on an axle like that doesn't mean that pulley is accelerating. The only way to make it spin, right, is if it's at rest, the only way to make it spin would be to exert a force somewhere off axis. So that's what the tension does basically here. So the tension is then the only force that we are going to put on my torque diagram. Again, we're starting nice and simple. So that tension, now look where I draw that on the torque diagram, right? I draw it at the place of force application. So I want to see that in your torque diagrams, that you're depicting the physical situation exactly how it is, right? Exactly where the force is applied and in the same direction the force is applied. So sometimes I see students like simplifying that a little bit. I would encourage you, don't simplify it. I mean, we're already going to be looking at really simple cases. This is an intro class and, we only have a little bit of math to work with. So don't simplify further. So there's my force. Then the other piece of torque is, of course, drawing in my r vector. Now, r goes, remember, from the axis of rotation to the point of force application. And r is a vector, so the direction matters. It's going to change the direction of your vector product if you draw your r in backwards, if you draw it in from the force application point toward the axis of rotation. So it's really important that you always remember that when you're drawing that r, you're drawing it from the axis of rotation, wherever that may be on the body that you're studying. Okay, so pulleys are sweet because the relationship between the radius here, the R value, and T is at a right angle. Can you kind of see that there? That's always going to be the case when you're working with a pulley. So that makes your math a little simpler, which is kind of cool. Pulleys are neat that way. All right, so what I can do is I'm going to apply then second law as we normally do. I'll apply that to the block, where I know that P minus T is going to be equal to MA for the block. And then if I look at the pulley, now I'm looking at second law, right? So for the first thing that I like for students to do is, before you start going to your second law, is actually to calculate the torque. So if I were to do that in this case, the torque that I have here is going to be that value R, right, which is actually a given value. Let me just cross that. Let me cross R and T, right? Let me write it this way right now. Great. So this cross product, what does this mean we're looking at? It means we're looking at magnitude of R multiplied by the magnitude of T multiplied by the sine of the angle between them, which is 90 degrees in this case. So that, of course, just simplifies to R times T. Now, direction, though, we need to put a direction on here. This is a vector product. So right-hand rule, R crossing with T, that gives me a torque that is directed into the page. So what I'm going to say then, I like to do the direction of acceleration positive. For this, I'm going to say into the page is positive. And again, up to you. You get to choose your coordinate system. So I'm choosing, now I'm in 3 dimensions. We have to be now, right? So to the right and upward is positive, and then into the page is positive. Again, the direction of alpha, right? The direction of angular acceleration is going to be into the page here. So we can get to alpha by now looking at our second law. I'll do that in a different color just to differentiate that. So if I look at my second law stuff, I see that the sum, second law tells me that the sum of torques is equal to I times alpha. So I'm looking at that equation up there on the top right. So what that looks like is RT equals I, that's the moment of inertia of the pulley, times alpha. All right. So I now have two equations, one that I rendered from my second law analysis of the block and one that I rendered from torque analysis on the pulley. And I have to use these two equations together now, right? These are my two equations. There's one little thing I'm missing here though, and that is like, how do I relate A and alpha? So we still need to think about that. So think about for a moment, how do alpha and A relate? We can add that to our list of equations if you want. All right, so relating A and alpha here. Now we're being asked to solve for alpha. So what I want to do is I want to substitute in for that in my block equation. We're not being asked to solve for A. So what I'll get here is tension equals P minus MA minus alpha R. So I'm just subbing in alpha R for A there. And now it's these two equations, right? These two that I'll use together and solve for alpha. So you can do some algebra there. Two equations, two unknowns. Tension is not one that we want. We're looking for alpha. So if we do that, then we can solve for alpha. And we should get PR over I plus MR squared. And that is our expression for alpha.